Hey guys, good afternoon. So Digby again here to discuss to you an alternative solution on how to conduct real-time analysis using equilibrium method. So equilibrium method has some uh, complications when it comes to the application of the solution on real-time analysis, and we really need to understand first the concept uh, because it's a little bit confusing, no? Unlike one dimension, one-dimensional linear elements like rings of columns, no? The equilibrium method is far better to use. But in case of slabs, the virtual work solution rather may be favored because of its being systematic, while equilibrium is like a classical theories to be understood upon its application. So, the legal method is founded on some uh, assumptions. So, namely, the analysis is based on equilibrium of individual elements. Okay, so when we say uh, elements, we are pertaining to individual slab segments. So, one equation per segment can be derived normally by taking moments about a suitable axis. So the choice of your axis of moment or rotation is really the key, not to maximizing the advantage of the method. So sufficient equations was written to determine unknown dimensions and ultimate rules. And unlike triple work solution, you don't need to worry about uh, more involved mathematical tool like optimization and differentiation. So torsion and shear forces are included in the equilibrium equation, although we know for a fact that uh, this torsion and shear will actually counteract each other or actually counteracts one another when we are using the equilibrium solution. But since this is an equilibrium method, we have to deal with the shear forces and to come up with a moment equation and satisfy the equilibrium condition. So the determination of the shear forces is actually the most difficult part. So we have to understand now how these shear forces are determined by considering a typical slab panel rectangular panel, which are actually identified or modeled in terms of its nodal description, okay, and the element description. Okay, for the nodal description, we're using uh, A, B, C, D, okay, as your notes. And for your element description, we're using numbers 1, 2, 3, 4. So this is actually the real or actual shear distribution when we're talking of slag segments. No? If we want to get the shear forces along the yield lines, so the yield lines, then the actual distribution of shears is uniformly uh, assumed to be uniformly distributed along the yield lines themselves. And we can actually simplify this distribution into a nodal distribution by using the nodal uh, directions AB, BA for QAB and QBA assure uh, shear forces contributed by the yield line B, QBC and QCB for the yield line BC, and QCD, QDC for the yield line C. Okay, so this is one way of uh, getting the nodal forces, or nodal shear forces in terms of uh, the yield lines. Okay, the yield line directions A, B, B, C, and C. Or we can also use another nodal description in terms of the element. So here we use the nodes A, B, C. So nodes A, B, C, and D actually uh, was used to define the nodal shear forces. But here we are using the element. Okay, so we are using here the element description assure, okay, combined with the nodal, okay, description. So node slash element uh, description. So this shear force here in terms of a capital Q is now uh, described in terms of the element 1 as your superscript. Okay, so this is superscript and a nodal letter subscript. Okay, so QA1 pertains to the shear force at node A contributed by element 1, and so on and so forth. Q at node B from element 1, Q at node C from element 1, and Q at node D for element 1. So to relate these two types of description, we can say that QB1 here at node B is actually the sum of the two nodal forces contribution of yield line AB and BC, QBA and QBC. Okay, so these are now the equivalent, no, of this type of description to this type of description. So this is a QC1 is equivalent to QCB plus QCB. Okay, so these are just descriptions that you need to understand because when we encounter them in literature such as this, we will be able to understand them easily to avoid confusion. Okay, so the nodal force is actually the total force uh, from sides meeting at the joint. Okay, so for Q1B, as defined here again, so this is simply equal to QBA plus QBC. So remember that we're talking here a single element alone. And the relationship of the equivalent forces on other segment is simply uh, similar, no, to what we normally do in beams, where there's a beam element with, of course, a uniform distributed load here. if we cut the beam into two, okay, here, so the shear forces now, shear here will be actually the same as the shear here. So this shear V here will be of equal magnitude but with opposite direction. Okay, so we know that the shear diagram here is simply something like this. Okay, so somewhere here is the shear. Okay, the shear force B that is defined in terms of segment 1 and segment 2 with equal magnitudes but opposite directions. So same is true with your relationship between segments 1 and 2. So your QAB, okay, contributed by element 1 must be equal to QAB contributed by element 2. Of course, in cases where the loads are always uniform distributed. Okay, for special cases wherein there are concentrated loads exactly at the nodes, then of course we need to add the effect of that nodal additional nodal force to compute the shear. Okay, so that's all for the introduction. I'll continue discussing to you more on the magnitude of the nodal forces on my next video. Thank you very much for listening.